Hello everyone, in this video we're going to be proving the monotone convergence theorem, which is essentially another characterization of completeness in R. And so the statement of the theorem is this, which is to say that if a sequence is monotone and bounded, then it converges. And we say that a sequence is monotone if it's either increasing or decreasing. A sequence is increasing if all the terms are at least as big as the previous term. It's decreasing if each term is at most as big as the previous term. So we have that an could be equal to an plus 1 could be equal to an, or otherwise it's less. So we're going to prove the monotone convergence theorem. We're going to prove it for the increasing case. It's pretty much identical for the decreasing case. So we'll maybe mention that after, but yeah, let's look at the proof. Well, okay, so first of all, what are we saying? So if I have a sequence in R, right, so this is my real number line, and we have some sequence, use a different color, xn in R, and it's monotone and bounded. So it's bounded. So that means, let's say there's some m, okay, it's bounded above. Some m, it's all less than this m. It's monotone increasing. So if it's increasing and it's bounded, that means that the sequence is doing something like this, right? We have A1, A2, A3, who knows, A4 might be right on top of A3, whatever. But then eventually it keeps going. And it must be zoning in on this upper bound. You know, it's bounded above. So we can prove that it must converge to this least upper bound of the whole set. You know, I mean, if m is the upper bound, then any number bigger is also an upper bound. So it's not fair to say that it'll always converge to its upper bound, but it'll always converge to its least upper bound in this case. And that's what we're going to prove. Okay, so let's take a look. So proof. Suppose an, greater than, should I say an plus 1 is greater than or equal to an for all n in n. Suppose also that an is less than or equal to m, which is some real number for all n in n. So we have a sequence. I guess, I could say an is a sequence of real numbers. It is increasing, right? It is also bounded above by some m. So what we can do is we can think about, let's let A be the set of all ANs. N, right? A is a subset of the real numbers. For all A in A, we have that A is less than or equal to M. And so we have that the supremum of A is a real number. Okay, and so we'll let S denote the supremum of A. And so the claim is that AN must converge to S. Okay, so proof of claim. Right, because we have claim, from this claim we're done, right? Because we're just trying to show that we took a sequence that was increasing and bounded above, and we showed that it converged. So really, that's the only thing left to do. So this discussion is just basically what I said already, right? Which is that if it's increasing and bounded above, then it must kind of zone in onto its least upper bound. So that's what I'm saying here. Proof of claim. Okay, so we need to show that, I'm going to use a different color here, right? So maybe I'll say show that for all epsilon greater than 0, there exists an n in n such that what an minus s is less than epsilon for all n greater than or equal to n. Okay, so what do we know? S is, a supremum. So what this tells us is that, for all epsilon greater than 0, S minus epsilon is not an upper bound for, we say AN, right? And so what that means is that there must exist some AN in in the sequence AN, or let's just say there must exist some N in N, such that, and maybe I'll put a little star or something, N star or N prime maybe, such that AN prime is greater than S minus epsilon, right? Because S minus epsilon is not enough. That's the characterization of the supremum, right? That if you take any epsilon, subtract it, it's not an upper bound anymore. There must be some element that is greater than S minus epsilon. Okay, but AN is increasing, right? AN is increasing, right? So what this tells us is that for all N greater than or equal to this N prime, AN is greater than S minus epsilon. So for all N greater than this N prime, AN must be less than S minus epsilon. I mean, because we are certainly less than S. AN is bigger. Did I say less than? Oops. AN is bigger than its S minus epsilon. So we have so far, let me just, maybe if I made a mistake there in what I said, let me just draw it. We have our AN, we have A, right? Or sorry, we have our S. And so we're taking some epsilon neighborhood, right? This is S minus epsilon. This is S plus epsilon. We're saying that there is an element of A, say right there, and there must be. And actually all of them after that have to be in that little zone right there. Clearly, as well, also, for all N greater than or equal to N prime, we have that AN is less than S plus epsilon, right? I mean, we actually have that for all. It doesn't have to be this. It could be, could just be 0 there. But notably with this, right? So for, N greater than or equal to N prime, we have that AN is between S plus epsilon and S minus epsilon, right? So that tells us that AN minus S, the absolute value of it, is less than epsilon. And there we go. We have it that AN converges to S. And we are done. All right, well, there's the whole proof. I kind of like putting it all in one screen after, just to see how long it is. Kind of takes up half the screen now. But there we go. So that is the monotone convergence theorem. That is all. Thanks for watching.